In the last class, we were talking about the saddle fixed points, and we had seen that there can be eigenvectors which would be the stable and the unstable eigenvectors locally. But if you look at the rest of the system, that means if you consider the state space outside the immediate neighborhood of this fixed point, you will find that these lines are all bent. So, it can be all sorts of possible ways they can bend, and we had said that this is the stable manifold and this would be the unstable manifold. Now, let us consider a few properties. Firstly, we know that in a dynamical system we can expect attractors. Attractors means starting from anywhere in the state space. If an initial condition starts from anywhere in the state space, they will ultimately be attracted to those collection of points. It can be a period 1 orbit, period 1 attractor, or period 2 attractor, even chaotic attractor, whatever it is. The point is that it is a collection, it is a set to which initial conditions are attracted. But there is no reason to believe that in a nonlinear system there can be only one attractor. At the same time, there can be more than one. For example, it is possible that here is one fixed point attractor and here is another period 3 attractor. Both are stable, right? Which means that both will have their own basin of attraction. That means there will be a collection of initial conditions which will be attracted to this one, there will be another collection of initial conditions which will be attracted to that one, and they would be divided by a basin boundary. Okay. So, let us now consider this kind of situations. In a dynamical system, there are all these possibilities. Now, if you consider there is one saddle fixed point with some kind of a unstable manifold and a stable manifold, then notice that started from any initial condition, say here, the orbits will be progressively attracted to what? How, suppose it is here, how will it proceed? It will progressively proceed like this. Started from any initial condition, say here, how will it proceed? It will proceed like that. So that it is not difficult to see that the orbits are attracted to the unstable manifolds, right. So, in initial conditions around here will be attracted to unstable manifolds. Now, that leads to the conclusion that if there is any attractor that must be situated on the unstable manifold of a saddle fixed point. Okay. For example, it may be so that a periodic orbit was stable for some time and then that became unstable, as a result of which period 2 orbit appeared, a period doubling bifurcation happened, and then there are now a period 2 orbit which is stable. The immediate conclusion would be that those 2 points of the period 2 orbit must be situated on the unstable manifold of that saddle fixed point. What am I referring to? For example, in the last class or the class before that, we had considered the Henon map, right? And we had seen that at a specific parameter value, it loses stability, the fixed point loses stability, and it becomes period 2 orbit. Okay. So, it is something like this, that earlier, let me draw here, earlier this point was stable and then now it has become unstable, and as a result of which there is a period 2 orbit which have become stable now, and this fellow has become unstable. Immediately the conclusion from this consideration would be that these two fixed points must be situated on the unstable manifold. So, this must be the unstable manifold direction. And as you know, further changing of the initial condition will lead to further series of period doublings, and finally it will land up into a chaotic orbit, and then the conclusion would be that even the chaotic orbit must be situated on the unstable manifold. Okay. So, if you find any system in which there is any attractor, that must be on the unstable manifold of a saddle orbit, provided there is a saddle fixed point existing. If there is no saddle fixed point existing, obviously that won't be true, but else it has to be on the. Now, notice another consideration. What is the property of the stable manifold? The unstable manifold is an attractor, that we have concluded. What is the property of the stable manifold? Just consider two fixed points, two initial conditions at the two sides of the stable manifold. What happens to them? Their further iterate will go like this, which means they would be repelled from the stable manifold, right. Initial conditions at the two sides of a stable manifold would be repelled from each other, will go in different directions. So, the property of a stable manifold is like that of a repeller, it repels. And where exactly do we need that property? We need that property in a situation like this, where you have one fixed point, another orbit, both coexisting, stable at the same time. So that you would immediately need some kind of a separation between them, a basin boundary, and the basin boundary must have the property that two initial conditions at the two sides of that must be repelled in two different directions. Okay. If that be so, then it requires the property that is already contained in the stable manifold. Does it stand to reason, therefore, that the basin boundary must be nothing but the stable manifold of a fixed point, which means immediately that there must be a saddle fixed point sitting on the basin boundary. Notice the line of arguments. I am talking in each sentence, but these are all individual theorems. So, there must be a fixed point sitting wherever you find two attractors existing at the same time, separated by a basin boundary. So, here is a basin of attraction of one attractor, here is the basin of attraction of another attractor, separated by a basin boundary. Immediately you have to understand that there must be, even if you do not know where it is, logic should tell you that there must be a saddle fixed point sitting there, and it should have the stable manifold here and the unstable manifold there, right. And the consideration that I just said, that all the fixed points must, all the stable attractors must be sitting on the unstable manifolds, means that this fellow must be sitting on the unstable manifold, and these guys also must be sitting on the unstable manifold, must be, there is no other way. Okay. So, you can see that from logic we can infer a lot of things about the character of the state space simply by logic. We did not know where this fellow is, but from logic we infer that there must be one. We did not know actually how the stable and unstable manifold go, but from logic we infer that they must be going through those points, and if there is a whole complicated chaotic orbit, the unstable manifold must go through all of them, all the points, the whole chaotic orbit. Okay. these are two very important conclusions. These are the prime roles played by the saddle fixed points. That is why saddle fixed points are the centerpiece of complicated dynamics. So, wherever you find very complicated dynamics, you know that it must be the handiwork of some saddle fixed point. So, first conclusion, let me write down clearly so that it goes into your head. One is that stable manifolds form the basin boundary. Got it? Yeah. Okay. Now, let us understand some of the other interesting things that the stable and unstable manifolds do. Just recall in the last class when we considered the Henon map, we found that there are two fixed points, one fixed point sitting somewhere here, both are on the 45-degree line. So, I will draw to two different places, and this fixed point was, what was the type? It was a saddle. This fixed point was, it was an attracting fixed point. We also concluded that beyond a certain parameter value, as you change the parameter value, this one also loses stability. Okay. Just recall, if you do not recall, just open that page and recall yourself. We have done that. Fine. So, this one was at some parameter value, both of them were bound, and when they were bound through a saddle node bifurcation, and this fellow was the saddle, that fellow was the node, and that node also became a saddle beyond a certain parameter value. So, beyond a certain parameter value, you would expect two saddles to exist, this and that. Okay. And this fellow was the attractor earlier, then it became a saddle, and this fellow was throughout a saddle. A saddle means it will have stable and unstable manifolds. Okay. So, it is actually the stable manifold and the unstable manifolds are something like this. So, this is the stable manifold and this is the unstable manifold. Consider a situation where this fellow is a stable fixed point. Can you infer where does this fellow go? It goes there, has to go there. Where does this fellow go? To infinity. Means that in the state space there will be some region that is the basin of attraction of this attractor, and there will be the rest of the regions which are the basin of attraction of the attractor at infinity. So, starting from any initial condition, say here, it will go to infinity. So, even though this fixed point is stable, it is not true that all initial conditions are attracted to this. There is a basin, and the basin boundary is created by the stable manifold of this fellow. Okay. Now, beyond a certain parameter value, this fellow becomes unstable. This fellow becomes unstable, and you have the period 2 orbit, then the period 4 orbit, and so on and so forth. You have seen the bifurcation diagram of this system on the computer. So, you know that it follows the same sequence of period doubling cascade, but at some point of time it also becomes chaotic. notice the important thing. Suppose you have a saddle fixed point here, and suppose here is the stable manifold and here is the unstable manifold, and as I told you that beyond a close neighborhood it will be bent, it will go any which way. So, supposing this fellow going like this, can it intersect itself? No. Why not? What is the logic? Why is this not permitted? No, wait a minute. Try to free yourself from the ideas that you learned from the continuous time dynamical system. This is the map. So, the kind of logic that you are probably going on in your head are actually taken from the continuous time dynamical system. At the same point, there cannot be two vectors. But here it is a map. What? Okay, let us do it with the attractor. Is it possible? Both are not possible, because if you have a point here, in the next iterate it should go along outwards from here, okay, and because it is here it should go outward from here. So, at the same time we cannot do both. So, that would not be permitted. Both these situations would not actually happen. It is not physically possible for that to happen. So, even though they wander any which way, they cannot really cross themselves. That is a limitation. But then, can this happen? There is no concrete logic that would prevent this, right? There is no concrete logic you can provide that will say that no, the stable and unstable manifolds cannot cross. They can cross. Now, notice a very interesting thing that happens immediately. Notice this particular point. Now, this point is both on the stable manifold as well as on the unstable manifold. Now, if you take this point and apply the map, it should map somewhere, and since it is the stable manifold, it must be along that direction, it must approach that. So, suppose it maps here, it must be on the stable manifold in next iterate, but it is also on the unstable manifold. How can that be possible? No, the only way that is possible is that unstable manifold also crosses. That is the only way it is possible. It cannot map to itself, because if it maps to itself, it becomes a fixed point. Fixed point was here, right? The only way that you can have this point mapping to this point is that this particular point where it mapped to, that must also be a point of intersection between the stable and the unstable manifold. Next point, say here, that must again be, and if there are a infinite number of points, it goes like this, right? All this must be so a single intersection between this stable manifold and the unstable manifold immediately implies, as a theorem, that there are infinity of intersections. A single intersection means an infinite number of intersections. Okay. Notice I am not doing any mathematics, just geometric logic. Is the proof convincing? Okay.
So, where does the point go then? The intersection point, where does it go? It goes to the
Well, it maps wherever it maps to this particular point, wherever it maps to, that must be a point again both on the stable manifold as well as the unstable manifold. So, the unstable manifold must go like this, has to. Not only that, where did this come from? It must have come from some place. That means, it must have been somewhere else in the previous iterate. Okay. Fine. Yes, which means that supposing it was here, because this is the unstable manifold, it goes in that direction. Suppose it was here, what does it mean? It means that this fellow has to turn around and intersect, so on and so forth backwards. So, both the forward iterates as well as the backward iterates should undergo an infinite number of intersections. Do you understand the incredible amount of complexity that gives rise to? These manifolds, so far they seem to be very benign stuff, only bend and twist this much, that much, but now the moment there is one intersection, there has to be an infinite complexity in the structure of these manifolds, right.
So the amplitude of these intersections?
There is no amplitude. Actually, these are all, this amplitude you are talking about?
Yes.
No, these are all schematically drawn. I have schematically drawn. The point is that how do we actually plot these stable and unstable manifolds? As I told you, you take the eigenvector, take a point on that eigenvector and see where they map, and then take many points between these 2 points and see where they map also, and that way you can trace the whole thing. So, I have schematically drawn, it might actually be like this or small amount of, but whatever it is, there must be an infinite number of intersections, that is guaranteed. Now, if this fixed point, the fellow which is at the center of this whole business is this one, which means the one that was earlier stable now it has become unstable, the one that is at the center of the center of the thing that is ultimately going into chaos. Okay. What will it lead to? The moment you have this, immediately you know that there are infinite number of points. Okay. What kind of attractor can there be in which there are infinite number of points? A chaotic attractor. So, if there is a homoclinic intersection, notice here the homoclinic intersection has a different connotation from the homoclinic intersection that you came across in continuous time dynamical systems. Here a homoclinic intersection has very specific definite meaning, that a homoclinic intersection immediately implies the existence of a chaotic orbit, existence of a Smale horseshoe. Just consider a neighborhood of this and check out what happens in future iterates. You will immediately find that that has to go through Smale horseshoe kind of stretching and folding. So, the point is that if there is a intersection between the stable and the unstable manifolds, that leads to chaotic orbit. What about this fellow? The fellow who was sitting not in the orbit, but on the basin boundary. There was another fellow sitting here. There was another fellow sitting here which was not on the orbit. It was on the basin boundary. That was also a saddle, and its stable and unstable manifolds can also intersect, right? When that happens, what will result? When the stable, suppose the stable manifold goes like this, say it ultimately has to go here. So, let me draw it at least politically correct diagram, because this has to go, otherwise somebody might raise the question, and this fellow say it goes like this. So, at some point of time they may intersect, right. If they do, what will happen? Immediately there should be an infinite number of intersections between these, means the basin boundary becomes infinitely complicated. Okay. The basin boundary becomes infinitely complicated. In other words, it becomes fractal. So, this is the mechanism by which we have fractal basin boundaries. Let us illustrate that using a program that we have. It is called Dynamics. It is written by James York of University of Maryland. Let me show from the start so that you can see how it works. So, this is Dynamics written by Helena Nusse and James York, and in the there are few menus available, and if you type out the name written here, it will take that particular map. In this case, you can see that H stands for the Henon map. So, H is the Henon map. Here it writes Henon map. Probably it is writing too small, so you might not be able to see. Nevertheless, so you remember the Henon map. You open that page. Okay, how did I write it? X n plus 1 is equal to a minus x n square plus and y n plus 1 is equal to x n. And we had done the exercise the last day where we had obtained the two positions of the fixed points. For what parameter value? 0. So, b is equal to 0.4, but a is equal to, we calculated it for some parameter values. Minus 0.09. Before minus 0.09 there was no fixed point. Beyond minus 0.09, say a is equal to 0. What did we conclude? What should we conclude? What should be the behavior? Two fixed points. Okay. So, I will see the parameter menu. Okay. C1, I will set it as minus 0. Okay. Now, A would be our, in this program the variable parameter is called rho. So, I will set rho as 0. Here it plots the basin of attraction. Now, you notice I will increase the basin resolution. But if I make it too high, then it will be a problem. You will not be able to see. Yes, it is reasonably good. Notice that still there is a basin of attraction for this fixed point situated here, and there must be another. The moment you see a basin boundary, your immediate instinct should tell that there must be another fixed point sitting on the basin boundary. You knew that there was another fixed point saddle, but you do not know where it is. Looking at the picture, you must know that okay, this must be somewhere. Where? Now, in order to calculate where, this program has a interesting facility, that is, if you press II, then can you see two crosses? One cross is here, small cross, a big cross is here. So, actually my position is there, and it is automatically showing where is my next iterate. It is called the image of that point. So, if I now move this point, see the other one is moving. Can you see? Fine. So, they are approaching each other. So, I note that there is a fixed point sitting quite there. Can you see? When they intersect, when they coincide, you know that the fixed point is there. That is a nice way of graphically calculating the fixed point. Okay. Now, one fixed point is there, I know. Where is the other fixed point? It must be somewhere on the basin boundary, and both the fixed points are on the 45-degree line. So, logically I expect it somewhere here, right, on the 45-degree line. So, let us go there, and I go down further this way, further down. Yes, we are close, right? So, we had calculated, we found that it is there. Huh? So, I will initialize it here. Now, I can go close to the point, it is here. What I did was, after coming close to that point, one can actually locate the point by a simple Newton-Raphson solver. So, I gave that as the initial guess, and the Newton-Raphson solution gave me the position of the fixed point. This is quasi-Newton method of 10 steps. If you write the quasi-Newton steps, it also gives the eigenvalues. You can see one eigenvalue is 1.47, which is an unstable direction, and this is minus 0.27. Okay, that is stable direction, and the eigenvectors are also given. You can easily calculate it that way. Okay, fine. Now, we are here. We had actually guessed our position, so we traverse this way, but nevertheless we are here. At this point, I want to calculate the unstable manifold to the right, the one that is that will go here. So, unstable manifold to the right, to UR. See, it has started from here and it has gone exactly to the fixed point, right. That confirms our initial theoretical structure, that it must go actually to this point, right. The one to the left should go to infinity, and this is actually, what is this? That is a stable manifold, and the stable manifold turns and goes this way. Happy? Okay. What was the parameter value at which this fixed point became unstable? 0.27. Okay. So, let us choose a parameter value slightly bigger than that, say 0.28. Okay. So, rho 0.28. Can you see, now there are 2 points. In order to convince ourselves that these are really the 2 points, let us start from this initial condition, and let me change the color. Okay. Now, these points probably are not visible. I started from this point. First iterate was here, the second iterate was here, third iterate was here, fourth iterate was here. It was actually going to this fixed point and then going this way, and finally it merged onto this. Okay. So, here are 2 fixed points, it has now become a period 2 orbit. If we increase the parameter further, it was 0.28, let us increase it to 3, no, 0.3. Still period 2, 1, 2. Can you see these 2 points? No. Okay, let me reduce the basin resolution. Now can you see? Okay. So here are 2 points, quite clear. By the way, how is this program plotting this basin of attraction? You can easily write this program. What it is doing is it has taken a box on in the state space, starts from one point in the box, goes on iterating it, and if it exceeds a certain circle of radius, there is some pre-assigned radius, very large radius, in some iterates it says that it is actually going to infinity. So it is true that you might question, how do you know that it will not come back and stuff like that, but nevertheless it is a reasonable estimate to say that beyond a certain number of iterates, if you find that it has gone beyond a certain big circle, it is going to infinity. So if that happens, that particular initial condition is given a color. Go to the next one, go to the next one, go and come here, it is actually remaining fixed, remaining stable. So it is given a different color. That and where it ultimately stabilizes, those things are also plotted with a different color. You can easily write this program, it is not a big deal. Now let us increase the parameter further, say 0.4. Still it is period 2, rho 0.5, still it is period 2. You can find out where the period 2 orbit will become unstable, but the calculation will become a bit untidy. So let us do it by this way, 0.6, still period 2. Still period 2. Well, now let us do a relatively quicker thing, draw the bifurcation diagram, so that from there I will know what is the parameter necessary in order to get something more. Okay, so BIFR is the bifurcation range, we will set from 0 to 2, large range. Oops, color. I want a is it visible now? Okay, how do I make this visible? Anyway, here that it has gone into chaos is more or less visible, right? So I can see that the range has to be less 0 to 1.5. Oh, probably is it is white on black, that's why you are having problem, is it? Okay, let's see. Is it better visible now? No. Let me increase the resolution. BIFR, now BIFE. Bifurcation values and BIFT. Probably these points are now better visible, is it? Huh? Yes. Okay. Now you can see that it remained period 1 till some value, and then it came here. At this point, the period 2 orbit became unstable. So in order to get a period 3 orbit, this whole range is 0 to 1.5. I guess I need to go to about 1, not less than that. Okay. So, rho 1. Okay. So, now we have 4 pieces already, rho 4 points at 0.9. Beyond that, what do we expect? Okay. Beyond that, it will go through very quick period doublings, and very soon it will land into chaos. So, if you see first period doubling, second period doubling, and then chaos. But notice what is the situation here. It should be, say you are choosing a parameter somewhere here, it should have 1 piece, 2 piece, 3 piece, and 4 piece chaotic orbit. Okay. So, if I choose the row somewhere 1, it will have 4 pieces of chaotic orbit. But what was our conclusion then? All these 4 pieces must be on the unstable manifold or the fixed point that must be sitting here. Okay. So, let me check. So, these are the 4 pieces. Let us check if they are really sitting on the unstable manifolds, because we always need to convince ourselves that we are really on the right track. So, I have pressed I, which means that I will be able to, I expect the fixed point to be somewhere here, because it has to be on the 45-degree line. So, it goes and finally see they are coming close. I have to go a little up, I think. Yes, we are reasonably close. Oh, very close. Fine. Well, it has found the eigenvalues as minus 1.7 and 0.23. It is a flip saddle. So, we are here. Now, I want to plot. Which one do you want to plot? The unstable manifold to the left or the right? Let me plot the one that is to the left, U L. See, starting from here, the unstable manifold has gone this way, turned around, gone this way, and as a result it does contain this piece and that piece, right. And if you draw the one that goes to the right, you will find that clear. Okay, let us also, we can also plot the one that is to the right, but you can easily guess that it goes this way, and you can also guess that as you increase the parameter further, there must be a parameter, a situation where it just intersects. देखते हैं. Well, has come very close. It is now a chaotic orbit. You can see that. If you want to plot it exactly, the chaotic orbit looks like this. And this is the basin boundary, means the fixed point must be sitting somewhere here, and this is the stable manifold. It has gone round and it is going like this, and here is a very close situation which is close to the. Now, what do we expect will happen when they intersect? Some parts of this orbit will fall in the both basin bound within in the basin of attraction of the attractor at infinity, right. When this fellow goes this way, what will happen? Some part of the basin boundary will fall there. Let us see what happens. very close, almost touching. Next, now it is rho is 1.2. I will make it 1.25. See what happens. No attractor. So there was an attractor so far. Suddenly it vanished. Why did it vanish? Because a part of the attractor intersected that and it went into the basin of attraction of the attractor at infinity. So every initial condition ultimately goes to the infinity, and therefore the attractor that was so far stable suddenly loses stability. This instability, notice that it is not the instability related to an eigenvalue. You cannot predict this instability simply by looking at the immediate neighborhood of any initial condition, any fixed point. It cannot be, this instability cannot be inferred from any linear system stability, but it still become unstable. This is a completely new class of instability that is called a crisis. A crisis, this is called a boundary crisis, where the attractor intersected the basin boundary, attractor itself intersected the basin boundary. It is called a boundary crisis. So this is one of the mechanisms by which a system may collapse. And it is the handiwork of the stable and unstable manifolds. It is just that they intersected. Okay. So is the concept of boundary crisis clear? Boundary crisis is created when the attractor itself, a part of the attractor goes into the in the basin of attraction of another attractor. But notice here the situation was that there was a attractor something like this, and there was a basin boundary going like this, and it intersected. Only this part has now intersected and gone to this side, right, which means that while doing the iterates on this, if an initial condition somehow falls in this part, then only it will go to infinity. Otherwise, it will keep on oscillating here. As a result, in a system that has undergone a boundary crisis, you can expect a very long transient, because only when an iterate falls here, then only it will go to infinity, else it will not, it will go on. Let us see, let us start from some initial condition in this situation. Let us start from some initial condition, say here, and do a see, I am look at the big cross, I am doing iterates. Oh, see, it is there, very much there inside, it is not going out, right. I am giving the iterates, no problem, it is still there. It will vanish the moment one point goes here, but before that it will still remain very much stable. Let me change the color so that it is visible more. See, now I am doing it fast. Oh, now it is suddenly gone out. So it has actually gone out in 296th iterate. And there are situations where the transient may persist for millions of iterates. For a million iterate you will find nothing is happening, it is still there, but then a particular iterate falls in a particular point and it goes to infinity, that is possible. So, this is a instability that can happen only in nonlinear dynamical systems and in situations like this. Okay. Let us recall the situation that we had in the logistic map x n versus x n plus 1. We had done it x n plus 1 is equal to mu x n 1 minus x n, this was the map, and we had done mu y 4. See, at 4, if you put 4 here, where does the middle point map to? 4, 0.5, 0.5, you get 1, which means this point maps to this point. If mu is greater than 4, it will be larger. As a result, this point will map to a point that is further this way, and as a result of which in the next iterate it will map here, in the next iterate it will go to the 45-degree line which is here, and then it will. So, what actually happened in this system also, though at the time of talking about it I did not make it clear, but there is a basin of attraction of the attractor, wherever the attractor is. The basin of attraction is the region between 0 and 4, 0 and 1. If you start from an initial condition that is outside this region, it goes to minus infinity. Okay. Now, it so happens that beyond this particular value of mu, a part of the chaotic attractor, especially the point that is at the top, that maps to a point that is outside this range, and therefore it goes to infinity. So, this is also a boundary crisis. So, what we have talked about here in this case is known as the often you will find that while if you draw a bifurcation diagram of a system, it goes on like this and finally it goes to chaos, but while it does so, a coexisting periodic orbit may be born. For example, suppose a coexisting period 3 orbit was born. How will it be born? How can it be? How can it happen? Through a saddle node. Now, as you change the parameter further, this will also undergo period doublings and stuff like that. These are pretty common situations where you have a big bifurcation structure, along with it some smaller ones, coexisting attractors coming into existence, but also going out of existence. Now, when they are there in this parameter range, they should have their own basins of attraction. At some points, at some parameter value, the basin of attraction of this one may touch this attractor, as a result of which what will happen, any initial condition that is here will ultimately go to this attractor, as a result of which this attractor will vanish, disappear. That is also a boundary crisis. Okay. That is also another boundary crisis. So, boundary crises are the mechanism by which a system ultimately loses its stability globally. Now, here we are not talking about the local stability, here we are talking about global stability. Okay, we will continue with that in the next class. Thank you.